This is Pat Kaplo. I'm solving problem number 4 on page 188 of the Giancoli textbook. The problem reads, a child in a boat throws a 6.4 kilogram package out horizontally with a speed of 10 meters per second. They reference the figure 7-31. Calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the child is 26.0 kilograms, and that of the boat is 45.0 kilograms. Ignore the water resistance. I've made a quick sketch here on the board. You can see that there's a boat, and the box has now exited horizontally over to the right. Let's go ahead and write some initial conditions. Some initial conditions might be the mass of the box. The mass of the box is given to us as 6.40 kilograms. We also know the mass of the boat. The mass of the boat is given to us in the problem as well, and that is 45 kilograms. And we also have the mass of the boy in the boat. The mass of the boy is 26 kilograms. And the only other piece of information that we have is the speed here with which the box leaves the boat. And we can say that that speed is given to us as 10 meters per second. And we know that it's to the right, so it'll remain positive. This particular problem can be identified as a conservation of momentum problem. It's a unique type of collision. One way you could actually think of it is kind of as an explosion. So you could kind of consider this here as our initial system, the box, the boat, and the boy all together at rest. They all have an initial momentum. We should know that it's at 0. And then after the event, in this case the explosion, if you will, the box exits over here in the rightward direction. And we expect the boat to kind of move in the opposite direction. We'll find out that the sum of the momenta in the system is still 0. Conservation of momentum laws have to be observed. That would be actually a really good way to start the problem, is by simply saying that the sum of the momenta in the system initially before the event must be equal to the sum of the momenta in the system after the event. So I've written that using sigma pi is equal to sigma pf. And now I can simply say that the momentum in the system might be the momentum of the box, the boy, and the boat together. I can just call that the momentum of the whole system together. Technically, we know that that should be equal to the momentum in the system after the collision. I can give them specific subscripts of 1 and 2. In this case, I'll say that must be equal to momentum of the boat with the boy in it, plus the momentum of the box. You should also recognize here, algebraically, that this whole concept of the system momentum, and you could have written this separately. I could have written this piece over here. I could have written that as the momentum of the box plus the momentum of the boy plus the momentum of the boat, and said that all of those individual momenta are 0. Box, the boy, and the boat, because initially they weren't moving. So I'm basically left with 0 is equal to the momentum of the boat plus the momentum of the box, which is, of course, moving rightward and out of the boat. I'm going to move the momentum of the boat over to the left-hand side, and I now get the momentum of the boat is equal to the momentum of the box. Both of these, of course, after the collision. Now, it's up to you to keep these things straight. One thing that might help is using the prime or those hash marks to denote that it was after the event took place. So I could go ahead and carry those through to help remind me that I'm specifically talking about the momentum of the boat and the momentum of the box after the box has been thrown. The explosion, or the collision, if you will. At this point now, I'm ready to actually plug and chug. I can first describe momentum as the mass times the velocity of the boat. So I can now say opposite mv of the boat is going to be equal to mv of the box, the mass of the box times the velocity of the box. In this particular problem, I'm trying to isolate the variable, the velocity of the boat. So I'll divide both sides by the term here opposite the momentum. Opposite the mass of the boat. So ultimately, my equation looks like this. I have velocity of the boat is equal to the mass of the box. I'm going to add these subscripts here now. I could have done that earlier. Times the velocity of the box divided by the negative mass of the boat. So at this point here, I'm good to go, and I'm ready to kind of plug these numbers in. I'll go ahead and do that on the next page. One thing regarding, before I kind of do that, one thing to keep in mind is that I've been talking about specifically the boat, but what we really mean is the boat and the boy together in the same. So they could be thought of as a single unit since they move together. The boy is sitting in the boat. So ultimately, this mass and velocity are going to describe both the boat and the boy together. So it's important to consider that when you add mass into the system. We're talking about the sum of the 26 grams. The 26 kilograms and the 45 kilograms. Those will give us a mass of the boy boat system together at 71 kilograms. Let's go ahead and move on to the next page here, and we'll go ahead and substitute. So finally here, the velocity of the boat, of course, the boat and the boy together, is equal to the mass of the box, 10 kilograms, times the velocity of the box, 10 meters per second, in the rightward direction. We'll maintain that as positive, divided by the negative value of the mass of the boy and the boat together, which when you add together is 71 kilograms. You're now left with a velocity of the boat, once you run that through your calculator, of about negative 0.90 meters per second. The negative sign, of course, indicates that the velocity of the boat is to the left. If I go back to that first page, we expect now that this boat here will be moving in the left-hand direction, or away from the direction of the box.